Okay, today we will discuss about the locomotion system used in the robot and continue with the locomotion. So the locomotion is characterized by a series of point contacts between the robot and the ground. Okay, so there is a point contact in case of leg locomotion. So we will also see some other type of locomotion like the wheel locomotion. Okay, so the advantages of a leg locomotion, they include adaptability and maneuverability in rough terrain. Okay, so they are more suitable for rough terrain, uneven surfaces. Okay, because only a set of point contact is required. The quality of the ground between those points does not matter. Okay, so point contact is there, so the quality of ground, that is not a main concern. So long as the robot can maintain adequate ground clearance. Yes, so in the surface, the ground clearance should be sufficient. If that is less, then leg locomotion will not be suitable for that type of surface or the terrain. In addition, a walking robot is capable of crossing a hole or chasm so long as its reach exceeds the width of the hole. Okay, so if the robot is moving and in the path there is a hole, so robot can across it, but it should be that the dimension of the hole, the length of the hole should be uh, within the range of the robot, between the two legs, the range of the two legs, or in one step. The distance covered by robot in one step, we can say that should be more than the length of the hole. Length, or we can say the diameter of the hole in case of circle. Okay, so a final advantage of leg locomotion is the potential to manipulate object in the environment with great skill. So there are the advantages which we have discussed in the leg locomotion robot. So an excellent example, that is insect, dung beetle. So it is capable of rolling a ball while locomoting as a result of its dexterous front legs. Okay, so this is something related to the biological counterpart in case of a leg robot. So the main disadvantage of leg locomotion include power and mechanical complexity. So this is a disadvantage, the power requirement and the mechanical designing, the joints which are provided for the complete locomotion system here in this leg type of locomotion. So the leg, which may include several degrees of freedom, must be capable of sustaining part of the robot's total weight. Okay, so it should be capable of sustaining the weight of the robot, and in many robots must be capable of lifting and lowering the robot. So up and down motion, like sitting, standing, so lifting and lowering the robot. So additionally, many high maneuverability will only be achieved if the legs have sufficient number of degrees of freedom to impart forces in a number of different directions. So these are some of the challenges. Leg type of robot, so single leg. So this robot is having only one leg, so it is not walking. Basically, it is hopping. Okay, so the robot must actively balance itself by either changing its center of gravity or by imparting corrective forces. So center of gravity, yes, because if it is changing, then the robot may fall. Whenever it is taking a position, moving from one place to another, it should maintain its center of gravity. It should change it so as to maintain stability. It should not fall in that case. So biped or the two-legged robots, very much common to the human being. Okay, so it can run, jump, travel up and down stairs, and even do aerial tricks such as somersaults. Then four leg. So although standing still on four leg is passively stable, yes, because higher the number of legs, then more stability we are getting. So walking remains challenging because to remain stable, the robot's center of gravity must be actively shifted during the gait because different four legs are there. All four should be coordinated, and as it is changing the position, the center of gravity that should also be changed. Then six legs. The six-leg robot configuration, they have been extremely popular in mobile robotics because their stability that is very high. With higher the number of legs, higher the stability. Okay, so it is preferred in that case. So it is clear that leg robots have much progress to make before they are uh, competitive with their biological equivalents. Okay. Nevertheless, significant gains have been realized recently, primarily due to the advances in motor design. Creating actuation systems that approach the efficiency of animal muscle remains far from the reach of the robotics. So as does the energy storage with the energy densities found in organic life forms. So a small comparison that we have to make it a counterpart, biological counterpart and the robot. We have to make them comparable or similar so that their performance should be the same, or the output which we are getting, that should be the same. Okay, so the development in the motor design, okay, then actuating system, okay, similar to that of the human. In the case of the biological counterpart, the muscle system that is the doing the task. Okay, similar type of systems we need to develop. So energy storage, energy density, all these have to be made comparable with the biological counterparts. Now, next type of locomotion, that is the wheeled locomotion. This is more popular and it is having a higher stability continuously. The wheel and ground, they are always in contact, because in leg we have to lift one leg, put on another point. So there's a point contact here. There is a continuous contact in the wheel locomotion. So the wheel has been by far the most popular locomotion mechanism in mobile robotics and man-made vehicles in general. It can achieve very good efficiencies and does with relatively simple mechanical implementation. So these are the advantages here. In addition, balance is not usually a research problem in wheeled robot design, because wheeled robots are almost always designed so that all wheels are in ground contact at all times. So continuously there is a ground contact. So stability is far better. So thus 3 wheels are sufficient to guarantee stable balance, although 2-wheel robots can also be stable. So here also the higher number of wheels ensure more the better stability. So 3-wheel robot, that is considered to be sufficiently stable. Satisfactorily, we can remove the stability or reduce the stability problem. So when more than 3 wheels are used, a suspension system is required in order to allow all wheels to maintain ground contact when the robot encounters uneven terrain. Yes, this is a big challenge, the uneven terrain. Okay, so it should be maintained. In case of wheel locomotion, that is a bigger challenge as compared with the leg locomotion. So we need a suspension system when using more than 3 wheels, so that the uneven terrain that could be maintained here by the robot. So instead of worrying about balance, wheeled robot research tends to focus on the problems of traction and stability, maneuverability, and control. So stability, okay, then traction, the moving, maneuverability, and control. These are the main focus areas here in the wheel locomotion system. So there are 4 major classes of wheels. So here, the type of wheels, they are represented: standard wheel, caster wheel. The first one in A, figure A, that is the standard wheel. B, that is a caster wheel. C is the Swedish wheel. D is the spherical wheel. So, according to that type, the first one, type A to D, the simplicity will is more in the first, then reduce in second, then third, then fourth. And similarly, that capability to move in different dimensions, that is also increased. So the type A, the standard wheel, that is the simplest one, but the steering capability, navigation, turning of the robot, that is limited. Then in type B, the caster wheel, it is more. In Swedish wheel, it is even more. Then in cylindrical wheel, the highest level of movement, motion we can get there. We can turn almost in any direction. Sorry, this the spherical wheel. Okay, the main advantage of standard and the caster wheel are easy implementation. Yes, simplicity is more in case of standard and caster wheel. The high load capability and the high tolerance to ground irregularities. So they are having these type of advantages. But these wheels are not inherently omnidirectional. Yes, they can omnidirectional means in any direction they can move. To make a vehicle using these wheels steerable, these steerable wheels depend on the wheel configuration of the vehicle, must be steered first along a vertical axis and then moved around a horizontal axis. So the steering capability, that is less in case of standard wheel and caster wheel. So especially in case of a heavy vehicles, and when it is not moving during steering, this steering method causes high friction and scrubbing during steering as the wheel is actively twisted around its vertical axis. So this increases the power consumption and reduces the positioning accuracy of the vehicle. Because of power, it's because of the friction, turning or the steering of the wheel, that becomes a challenge. Power consumption becomes more, positioning accuracy that also reduces. Then Swedish wheel, that is like a normal wheel, but it has little passive rollers around the circumference on the outer surface of this wheel. Also, there are rollers, passive rollers are there. So these rollers provide low resistance in another direction as well. So that problem, the friction there, that is reduced in the Swedish wheel. So depending on the angle in which the rollers are arranged, so the wheel is able to roll smoothly in any direction. The wheel's primary axis serves as the only actively powered joint, but it is possible to design with these wheels omnidirectional robots. Okay, so robot using this type of wheels, they are omnidirectional. They can turn in any direction. The spherical wheel is a real omnidirectional wheel. Now here in the spherical type of wheel, the steering capability or the omnidirectional advantage that is even more than the Swedish wheel. So the ball wheel mechanism is used to implement spherical wheel